Let's jump right into this explainer and trace a really fascinating journey. We're going from basic human decision-making all the way to the mathematical engines that actually power state-of-the-art artificial intelligence today. If you've ever wondered how computers learn to make choices without just, memorizing a giant math equation, well, you are absolutely in the right place.
So here's our roadmap for today. We're going to start with decisions, not just equations. Then we'll look inside a decision tree, figure out measuring uncertainty and purity, warn you about the danger of overfitting, and finally, we'll harness the wisdom of crowds.
All right, kicking things off with Section 1, Decisions, Not Just Equations. To really get this, we have to look at why we even needed a new approach to machine learning in the first place, right? For a long time, the absolute gold standard for predicting data was fitting mathematical equations to numbers. But, well, the real world isn't just about continuous numbers.
And this completely brilliantly illustrates the exact problem. While something like linear regression is great for fitting equations to continuous numbers, like, say, guessing the exact price of a house based on its square footage, it completely falls apart when a bank needs to make a definitive yes or no decision on a loan. I mean, you can't just draw a straight line to decide someone's financial future. You need a categorical decision, a hard yes or no.
Think about it this way. If you go to the doctor because you have a fever, they don't immediately start writing a complicated mathematical equation on a whiteboard to figure out what's wrong with you. No way. Instead, a doctor asks a sequence of logical questions. Things like, do you have a cough? Or have you traveled abroad recently? Or is your temperature above 39 degrees? And each answer naturally leads right to the next question. This is exactly the human process that inspired decision trees. Instead of forcing a computer to discover some magical equation, we actually teach it to discover the sequence of decisions that best separates the data.
Moving on to Section 2, inside a decision tree, it is incredibly fascinating how we can take that basic human logic and map it directly into a machine learning structure.
It's just like a physical tree, but, well, upside down. Every single tree starts at the very top with the root node. That's the single most important first question. From there, it splits along branches into what we call internal nodes, which are basically just the follow-up questions. And eventually, the data lands at a leaf node where the final prediction is made. It's kind of like walking through a maze where every turn is a simple yes or no, continually narrowing down the possibilities until you arrive at your final destination, whether that's loan approved or loan rejected.
Which brings us to Section 3, Measuring Uncertainty and Purity. Now, the crucial point here is, if the computer can ask any question, how does it systematically track down the single best question to ask first? If you have a data set with 100 different variables, it can't just guess. It needs a cold, hard mathematical strategy.
Imagine a node that is perfectly mixed. Picture a box filled with exactly 50 spam emails and 50 legitimate emails. This represents maximum uncertainty because predicting the outcome of the next random email you pull out is incredibly difficult. I mean, you're basically flipping a coin at that point. In machine learning terms, we'd say this node is highly impure.
But watch what happens when we ask a really good question. The data separates, the node becomes highly pure, and our confidence in the prediction just skyrockets. So if a node ends up with 90 legitimate emails and only 10 spam, the uncertainty drops dramatically. The entire goal, the whole shebang of a decision tree, is to transform mixed, impure groups into highly organized, pure groups.
To measure this transition objectively, researchers use something called entropy. It's this brilliant concept borrowed from information theory. Basically, high entropy means highly mixed data, while low entropy means pure data. The algorithm acts exactly like a detective, hunting for the specific piece of evidence, the right question, that drops entropy the most. It systematically removes suspects until only the truth remains.
And here's how that actually looks in practice. Let's take a wildfire example. We start with a highly mixed root node, which has an entropy of 0.97. Then the computer asks, is the burned area greater than 2,000 hectares? The data splits, and the weighted entropy of those new branches drops down to 0.72. So subtracting the entropy after the split from the entropy before the split gives us an information gain of 0.25. And that number right there, that is the exact amount of uncertainty we just destroyed. The tree will literally test hundreds of questions and always choose the one with the highest information gain.
Now, it's worth mentioning that many modern Python libraries, like scikit-learn, actually use something called the Gini index instead of entropy. Don't worry, they're basically just two different trails up the exact same mountain. The Gini index measures the probability of making a classification error. Because squaring probabilities is mathematically faster for a computer than calculating logarithms, the Gini index is often preferred when you're dealing with massive data sets.
but it achieves the exact same goal, finding pure groups.
Okay, Section 4, the danger of overfitting. So we now have this brilliant engine for reducing uncertainty. But what happens if we let the tree ask questions forever, like literally until every single leaf is 100% pure? Well, this brings us to a massive trap in machine learning. You see, every dataset contains signal, which are genuine, repeatable relationships, and noise, which are just random variations or totally random coincidences. Think of the signal as the beautiful music playing on the radio, and the noise as that annoying static. If a tree grows too deep, it actually stops learning the real signal and starts memorizing the random noise. This is a super dangerous flaw known as overfitting. The model gets 100% training accuracy because it basically memorized the answer key, but it leads to terrible, rigid predictions out in the real world. So to fix this, we have to act like a gardener and prune the tree so it stays flexible and accurate. We can use pre-pruning, which stops the tree from growing too deep in the first place, maybe by setting a maximum depth. Or we can use post-pruning. That's where we let it grow massive, and then we go in and ruthlessly edit out the weak, unnecessary branches later on. A simpler model that generalizes well is vastly superior to a complex model that just memorizes the past. Which perfectly leads us into Section 5, the wisdom of crowds. Because you know what? Even a perfectly pruned tree has its limitations. It only looks at the data from one specific perspective, meaning it can still make mistakes. Which brings us to the ultimate evolution of this whole algorithm. Have you ever seen a crowd try to guess the number of jelly beans in a giant jar? Some guesses are just way too high, some are way too low. But if you average all of them together, the collective guess is usually astonishingly accurate. Instead of relying on one tree that might make a mistake, ensemble learning relies on a diverse crowd of trees. It's very much like asking a panel of specialized doctors for a medical diagnosis rather than trusting just one single opinion.
This exact crowd philosophy powers the absolute best tabular AI models in the world today, and they generally fall into two main families. First, we have bagging, where we build hundreds of independent trees on different subsets of data and let them take a democratic vote. This is the famous random forest algorithm. And then we have boosting. This is where we train a sequence of trees, one after another, where each new tree is specifically designed to correct the mistakes of its predecessor. Algorithms like XGBoost and LightGBM use this boosting technique to completely dominate modern data science.
So we've traveled from simple flowcharts mapping human logic through the mathematics of entropy and information gain, all the way to massive self-correcting ensembles. As we wrap up this explainer, I really want you to think about the complex problems you face every single day. Are you relying on just one isolated perspective, like one single decision tree? Ask yourself how combining multiple, diverse perspectives could help you cancel out the noise, isolate the true signal, and help you make a perfect decision. Thanks so much for joining me on this deep dive.